Okay, can everybody see my screen that says periodic properties, atomic radius? All right, perfect. Thanks a lot. Well, let's talk about the trends across the periodic table in terms of atomic radius. And one of the things that we discussed last class was effective nuclear charge, right? We talked about ZEFF, which we call effective nuclear charge. And what it says here is that size, or atomic radius, increases going down a group. And the reason why atomic size increases going down a group is because the principal quantum number increases as we go down a group. And if you're like, what's principal quantum number? Well, if we were at the first period, this is where n is equal to 1. So I could have a 1s orbital, and then n is equal to 2. And we know that a 2s orbital is higher energy than a 1s. We also know that it's bigger than a 1s, right? And that is principal quantum number, or as n increases as we go down the periods, right? The orbitals get bigger and bigger and bigger, and the electrons get further and further away from the nucleus. And so that is why atomic radius, generally speaking, increases as we go down a group. Now, you notice in the transition metals, there aren't very big changes going down the groups of the transition metals, but you can see that if you look at the group 1A elements, or let's say you look at the group 3A elements, it's very clear that there's a trend that the atoms are getting bigger and bigger as the principal quantum number increases. Now remember, when we're talking about periodic properties this evening, you are responsible for knowing the trends, okay? Not every exception to every rule. Yes, the book goes into some detail about exceptions, but I'm not going to ask you about, every exception. If there's an exception that I expect you to know, I will let you know very clearly that you're responsible for that exception. But again, you want to be aware of the general trends, and that atomic radius increases going down a group or a column or a family, whatever you want to call it. Well, what about when we go across a period? Well, if I go back here to this figure, I think it's pretty evident that as we go across a period, let's say we're going from lithium to beryllium, so on and so forth, all the way over to fluorine, it's pretty obvious that size is decreasing in this direction, right? So we could say here size decreases. And the figure that's on the next slide is simply a graphical representation. You see that on the y-axis, we have atomic radius, and then down here on the x-axis, we have atomic number. So let's say you start with hydrogen, which is on the furthest left, and you drop down to helium. Well, helium is smaller than hydrogen. Helium has a higher atomic mass, but why is helium smaller? Remember, it's based on effective nuclear charge, right? An effective nuclear charge is equal to atomic number subtract shielding electrons, or the number of shielding electrons. And we said that for our purposes, we said that effective nuclear charge was pretty much or close enough to be equal to atomic number minus the number of core electrons. So core electrons. If we look at the second period, starting with lithium, you can see that lithium is the biggest, okay? And as we go across to neon, you can see that the general trend is to decrease in atomic radius. Why is that? Again, it's based on effective nuclear charge. Let's think about what's happening as we go from lithium to beryllium to boron to carbon, so on and so forth. As we go across the second period, so I'm just talking about lithium to beryllium, I'm talking about this part of the whole picture right here. As we go across, the number of core electrons remains the same. Core electrons are the non-valence electrons. So for any element that's in the second period, the core electrons are going to be 2, just the 1s2 electrons, right? Okay, so as we go across that period, we're adding more and more protons to the nucleus. Okay, the inner electrons, or the core electrons, do a good job of electrons, but when we add more valence electrons, they do a poor job of shielding each other. And so as that nucleus gets more and more positively charged, the valence electrons are going to feel more of that big positive charge, or that growing positive charge, so to speak, in that nucleus, and that's going to pull the valence electrons in tighter and tighter and tighter. Again, I made sure to talk about this with you during the last lecture, that it's a little bit counterintuitive, and we see the same trend. Let's say if we're looking at, going from sodium to argon, this is the third period. right? As we go across, the number of core electrons doesn't change in the third period. We always have 10 core electrons. And at sodium, we have 3s1. At magnesium, we have 3s2. At aluminum, we have 3s2, 3p1, right? Those are the valence electrons, the ones with the highest principal quantum number. But the number of core electrons would always be 10. And so again, the core electrons are good at shielding the positive charge of the nucleus, but as we add more and more valence electrons, they don't do a good job of shielding. And so as the nucleus gets more and more positively charged, it's going to rein in or pull in those valence electrons a little bit more. It's going to pull them in tighter and tighter. So this is a summary of what I just said. Valence electrons are strongly shielded by the inner electrons or the core electrons, but they're only weakly shielded by other valence electrons. So as we add more and more valence electrons, not core electrons, but valence electrons, as we go across a period, we see that effective nuclear charge is going to increase and the valence electrons will be pulled in tighter and tighter. Across a period, effective nuclear charge increases faster than shielding, resulting in contraction of the atomic radius. This figure down here shows three different axes. We have atomic number down here. This is for the third period. So these are third period elements, okay, going from sodium to argon. And you can see that as the atomic number increases, what's happening to effective nuclear charge? It's increasing. And then what's happening to atomic radius? It's decreasing. The main thing is that you understand the point, or the concept rather, behind effective nuclear charge. And that you know that as we go across a period from left to right on the periodic table, the size of the elements generally decrease. And as we go down a group or a family, that the size of elements increase. With that in mind, let's try a question. It says here, which atom would you expect to be larger, gallium or arsenic? So let's highlight these two elements. We got gallium, which is right here, and we have arsenic. So they're right next door to each other. Now you might remember that when you have two elements that are in the same period, right, gallium and arsenic are both in the fourth period. So this is n is equal to 4, right? As we go across a period, effective nuclear charge increases, right? And so what happens is that atomic radius decreases. And since gallium, did I circle germanium instead of gallium? I think I did. Okay, anyhow, there we go. And since gallium is further to the left, it's going to have a lower, or sorry, it's going to have a lower effective nuclear charge, and therefore it's going to have a smaller radius. All right, give me a thumbs up if you follow me on that one. Okay, good, because I solved that simply using a qualitative analysis, right? But we could also think about this in terms of a quantitative analysis, right? If we used our formula, effective nuclear charge is equal to atomic number, subtract the number of core electrons. Well, remember, since both gallium and arsenic are in the fourth period, the noble gas that precedes them is argon, and argon has a total of 18 electrons. So those are the core electrons. So that means my sigma for both of these, gallium and arsenic, is going to be 18. So if I want to determine for gallium the effective nuclear charge, it's going to be the atomic number of gallium, which is 31, subtract 18, which is 13. So that would roughly be my effective nuclear charge. If I do the same exercise for my arsenic, the effective nuclear charge is going to be the atomic number of arsenic, which is 33, subtract the same number of core electrons. And of course, you're going to end up with a higher number. So that means that arsenic is simply going to be smaller. All right? Anyhow, either solution works, but again, as long as you understand the concept, you will be good to go. All right, let's try another one that discusses atomic radiuses. Which atom would you expect to be larger, potassium or magnesium? Well, let's highlight those elements. We have potassium, which is right here, element number 19, and we have magnesium. which is element number 12. I'm going to throw this out there to my students. Does anybody have an idea about this one? Which one of these would be larger? Yeah, Trevor, Bruce, you're both correct. The answer is potassium. Why? Because remember, the size increases with principal quantum number. Magnesium is in the third period and potassium is in the fourth period. And so potassium is going to be bigger. And you might be thinking, well, whoa, Mr. Dion, these two elements aren't in the same group. They're not in the same family. Okay, they're not in the same family, but think about it. Even if we compared sodium and potassium, well, potassium's going to be bigger. And if we compare sodium and magnesium, magnesium's going to be smaller even than sodium, because remember, as we go from left to right across a period, effective nuclear charge increases, and thus the atomic size decreases. Well, you might have noticed that I didn't mention much about the size of the transition metals, and you probably noticed right away that there isn't a big difference in the sizes of the atomic radii of the transition metals, right? If you look, you can see the first two or three going from, say, scandium to titanium to vanadium right here. You can see they're decreasing there, but boy, it is not a big difference, right? If we look at the transition metals. Well, let's think about that. If we are talking about going across a row, right? If we're talking about going from scandium to zinc or from ytterbium to cadmium, what about those? Why wouldn't the elements get smaller and smaller and smaller? Well, let's think about it. Remember that when you go from potassium to calcium, here my N is equal to 4, but when I get to scandium, this is my N is equal to 3, right? I go from a 4s to a 3d. The same thing occurs here. I go from N equals 5, and I shouldn't call that N is equal to 3. I should do it like this. I should just call this N minus 1, right? And the same thing here, right? We get N minus 1. So we go from a 4s to a 3d, or from a 5s to a 4d. Well, what's the net result of this? Let's go back to our formula, which is effective nuclear charge is equal to atomic number approximately subtract the number of core electrons. Well, if we're talking about determining the effective nuclear charge for potassium or calcium, where are the core electrons? The core electrons are anything before there, right? It's 18 core electrons for potassium and calcium. But remember that the 4d electrons are going to have a lower energy than the 4s electrons. And because of that, when you start adding electrons here, right, not only is your atomic number increasing, but you're also increasing this, right, the number of core electrons at the same time. The electrons aren't valence electrons. The 4s electrons, let's say if you're talking about, let's say, vanadium, it would be the 4s electrons that are the valence electrons. Okay, so as Z increases, so does sigma for the transition metals only, and that is why effective nuclear charge doesn't change much going across the transition metals, and therefore there isn't a big difference in size going down or going across a period. Now, generally speaking, when we go down a group or down a column in the transition metals, it says here that increase in size going down a column. Well, I'd be hard pressed to say that there's a big difference in size going down the transition metals. Okay, they might increase in size, but very, very little. Anyhow, this just shows us a little bit more about atomic radii, and we discussed this during the last lecture. In a metal, the atomic radius is defined as 1/2 the distance between two nuclei in adjacent atoms. All right, so let's say the nucleus, maybe I should use a different color. The nucleus of one metal is here and the nucleus of another metal is here. Well, you measure that distance, okay? And then the atomic radius, which would be, maybe I'll use a different color again, would be this distance here, right? This is R. R is going to be equal to the distance divided by 2. So 1/2 the distance between the two nuclei in adjacent atoms. That definition applies not only to metallic atoms, but it also applies to covalent atoms, okay? Or atoms that are in covalent molecules. So if you, say, wanted to measure the atomic radius of bromine, which is a diatomic element, right? We all know that. We have Br2, like that. Well, the same thing applies. The atomic radius is going to be 1/2 the distance between the two nuclei in these adjacent atoms. This next figure shows the trend of atomic radii, or the sizes of atomic radii for representative elements. You notice that the transition metals would be in here and they're left out completely. So this is only S and P block elements. And again, what do you notice? Hopefully it's pretty abundantly clear here that as you go across a period, generally speaking, atomic size decreases. And that's because effective nuclear charge increases, right? Now, if you actually look at the values for effective nuclear charge going down a group, you'll see that they actually increase slightly. And the reason why is not important for our class at all. But what's important that you understand is that when we go down a group, it's effective nuclear charge isn't the dominant factor in determining the size. It's the principal quantum number. So higher N, or principal quantum number, larger atomic radius. All right. I like this figure. I think a picture is worth 1,000 words, and it's really good, just to look at this and kind of cement it in your mind. If you're the kind of person who has to see everything in the form of a graph, well, here you have it. This is basically the last figure, but shown in terms of a graph. So here we're increasing in atomic numbers here. So if you're like, why do they keep, switching here? Well, this is the second period. This is the third period. Down here, this is the fourth period, so on and so forth. What's the general trend? Of course, there's anomalies, right? There's all kinds of anomalies. I'm not going to quiz you about anomalies. I just want you to know that generally speaking, when we're looking at a group, like let's say we look at, a period, let's say we're looking at the third period, like this, what happens generally speaking as we go across the period? The atomic size decreases. I mean, if you wanted to look at a group, sure, you could do that too. If I circle all of these top points here, these are all group 1A elements. And generally speaking, what do you see as we go down the group, as we go from lithium to sodium to potassium to rubidium to cesium? Generally speaking, the atomic size increases because the principal quantum number is increasing. Well, we've looked at those quite a bit, so I figure that by now you are, probably with me on that. And let's try a sample problem to see if we can figure this out. It says, referring to a periodic table, arrange the following atoms in order of increasing atomic radius. Well, I'm not going to haul up a periodic table, but I will draw a little portion of the periodic table that has these 3 elements in it. So I'm going to draw something that looks like this. Okay, so this is group 5A. This is group 4A. It's group 6A. So we have oxygen and sulfur and nitrogen and phosphorus. And then we have carbon and silicon, like that. And the elements that we're interested in are phosphorus, silicon, and nitrogen. Well, what do we know about atomic radius? We know that atomic radius increases with principal quantum number. The second period, n is equal to 2, and then the third period, n is equal to 3. If I compare those two, any elements that are in the third period are going to access a higher principal quantum number, and therefore they should be bigger than any elements with a lower principal quantum number. And so if I arrange these from small to large, the smallest of all of these should be the nitrogen because it's in the second period. Whereas if I compare silicon and phosphorus, silicon should be the largest, right? Because we know that effective nuclear charge increases going this way, and therefore the atoms get smaller. So like that. And so silicon is going to be the largest of these, and then phosphorus is going to be somewhere in the middle, like that. Now, with all this looking and examining atomic radii, you might be wondering about ionic radii, right? We spend a lot of time talking about ions when we did nomenclature, and I spent a lot of time explaining why elements in group 1A form +1 cations, why elements in group 2A form 2+ cations. I explained why they do that. It's because they want to be isoelectronic with the nearest noble gas. Well, what if I compare the size of, let's say, sodium metal versus a sodium cation? Here they are right here. Here's sodium metal, and here's the sodium cation. Remember, sodium has one valence electron, right? 3s1. And so it likes to lose that one electron to form a +1 cation. If you notice, the x-axis is radius. And so Na plus is actually smaller than sodium, right? It's actually quite a bit smaller. And the reason why it's smaller is because, let's think about it. Did the number of protons in the nucleus change when we went from sodium to sodium plus, right? Absolutely not, right? Sodium has 11 protons. The sodium cation also has 11 protons. This goes right back to the beginning of our class where we discussed that the identity of an element is determined by the number of protons in its nucleus. What about the number of electrons? In my sodium, I have 11 electrons, right? If I have 11 protons and those are positive and 11 electrons and those are negative, well, they balance out each other. And sodium has a charge of 0, right? Pure sodium. We leave that 0 superscript out, but we know that it's neutral. What about in the sodium cation? It lost an electron, therefore it's got 10 electrons. Let's think about this really, carefully. The amount of positive charge in the nucleus didn't change. But now when I have the sodium cation, I've got less valence electrons. That means I have more positive charge per negative charge, and therefore those 10 electrons, they're going to feel more of the positive charge in that nucleus, and they're going to pull it in, and it's going to become smaller. All right, there we go. Give me a thumbs up if that concept makes sense. The nuclear charge remains constant, but now we have less electrons per positive charge, and therefore they're going to be held even tighter. Okay, great. Well, if you understand that concept, you probably can figure out, what's going to happen if I say compare, chlorine with chloride. The opposite is true. Look, if I compare chlorine and chloride, how many protons does chlorine have? It's element 17, so it must have 17 protons. In just plain old chlorine, it's got 17 electrons, but in chloride, it's got 18 electrons. Did I put piece when I meant electrons? Mr. Dion's getting ahead of himself. Okay, there we go. Anyhow, so let's think about this. I can give you two good reasons why chloride should be bigger than chlorine. Number one is the first one that we discussed, right? The amount of positive charge in the nucleus remains unchanged, but now you have more electrons, you have more negative charge per positive charge. And so the electrons are going to feel less of the positive charge of the nucleus, and they're just not going to be held as tightly. I'll give you another good reason. Think about it. If I have, in chlorine, I've got 7 valence electrons. I have 3s2 and 3p5. When I add an extra valence electron, not only does it feel less of the nuclear charge, it also has electron-electron repulsions, right? So they're going to try to spread out to get more space. The net result is this. When we're comparing cations and anions, a cation is always, no exceptions, going to be smaller than the atom from which it was formed, and an anion is always going to be larger than the atom from which it was formed. Look at lithium and fluorine when they react, right? If I think about the electron configuration of lithium, which is helium 2s1, and the electron configuration of fluorine is helium 2s1, 2s2, 2p5. Right? If lithium loses that one valence electron and gives it to the fluorine, they're both going to be isoelectronic with a noble gas, won't they? Right? The lithium plus is going to be simply isoelectronic with helium, which is a noble gas. And the fluorine is going to be 2s2, 2p6, which is the same electron configuration as neon. So now they're both isoelectronic with a noble gas, but look at the difference in the size, right? The lithium shrank because it's a cation, and the fluorine got bigger when it became fluoride. Here are some more examples. And there's a very important concept in here that I need you to understand before we can move on. And that's, what about having more than one charge, right? Let's compare these two right here. Let's compare sodium and magnesium, those two ions, plus cation, 2 plus cation. If I compare sodium plus and magnesium 2 plus, how many protons are in the sodium nucleus? 11, because it's element number 11. How many protons are in the magnesium nucleus? 12, because it's element number 12. But they both have the exact same number of electrons, don't they? They're both isoelectronic with neon. That means they both have 10 electrons. Now let's compare very carefully. If the number of protons is increasing and the number of electrons is remaining constant, what does that mean? That means that in magnesium, the 2 plus cation, there's going to be more positive charge per negative charge, and it's going to pull those electrons in even tighter. So that's why the higher the charge on the cation, the smaller it's going to be. The opposite applies for anions. If I compare these three anions here, nitride, oxide, and fluoride, right? They're all isoelectronic with neon, aren't they? If I compare N3 minus, okay, how many protons does it have? It's got 7 protons. If I compare O2 minus, how many protons does that have? It's got 8 protons. How many protons in fluoride? It's got 9 protons. But they all have the exact same number of electrons, don't they? They all have 10 electrons. And so as the number of electrons remains constant, but the nuclear charge is increasing, it stands to reason that as you go across from the nitride to the oxide to the fluoride, that the atomic radius should be shrinking. I'll give you another reason why. Okay, they all have the same number of electrons, but think about N3 minus. You've got more electrons in the valence shell repelling each other. They're going to take up more space. All right. Before we can leave this slide, there's one more concept I need you to understand, and that's with transition metals that have more than one possible charge. Okay, I could have, put copper in this funny looking box here, but I'm choosing to go with iron. Okay, so I'm comparing iron 3 plus and iron 2 plus. Which one of those is going to be smaller? Right, iron 3 plus is going to be smaller. Right, so the more positively charged the cation becomes, the smaller it is. The more negative the anion becomes, the larger it is. Well, with that in mind, let's take a look at a problem where we're asked to compare sets of ions. For each of the following pairs, indicate which one of the two species is larger. We'll start with A, nitride and fluoride. Let's think about their electron configurations. For nitride, the noble gas that precedes nitride or nitrogen is helium. Okay, so it's going to have helium 2s2. It's going to be 2p6. The same thing applies for fluoride, doesn't it? It's got the exact same electron configuration. Helium 2s2, 2p6. Remember, you might be looking at these two and saying, hey, they're identical. They're the exact same. No, they're not, because they have different numbers of protons, don't they? Well, based off of that, could somebody tell me which one of these is going to be larger, N3 minus or F minus? Absolutely. Julius has it. It's the nitride is going to be bigger because when I'm comparing two elements or two ions rather that are isoelectronic, whichever one has the more negative charge is going to be bigger. If I compare the magnesium cation and the calcium cation, well, you notice that in the periodic table in group 2A, this is group 2A, I go from beryllium, not bromine, to magnesium to calcium. And so even though they've both lost 2 electrons, the magnesium will still be in a lower principal quantum number than the calcium ion. And so the larger one is, of course, going to be the calcium. All right, and we already looked at the last one. It was the last thing I answered or showed you. And I said that the more positively charged your cation becomes, right, the smaller it's going to be. So let's say this is the radius of your iron 2 plus cation. Then the radius of your iron 3 plus is going to be even smaller like that. Okay. Let's switch gears and get into a new topic. The topic is called ionization energy. It's obviously got something to do with ions. And it's a definition that you simply need to memorize. It's the minimum amount of energy required to remove an electron from an atom in the gaseous state. Okay? Technically, I could even do better than this definition here. It's the minimum amount of energy required to remove 1 mole of electrons from 1 mole of the element or the atom in its ground state. Okay, so if you think about any element, and I know it says I all over the place here. It's not just talking about iodine. It could be any element. Okay, you take an element, it's got electrons. Okay, let's say it's nitrogen, for example. Nitrogen has 7 electrons. Well, first you remove an electron. Okay, so you say the first ionization energy is that element in the gaseous phase, and then you remove an electron, and of course you end up with a gaseous cation. Okay, well, there's a certain amount of energy associated with ripping that electron off. But now you've made a cation. So what happens when we go from X, right, element X to X plus? It gets smaller, doesn't it? And those valence electrons are going to feel more of the effective nuclear charge. And so the second ionization energy should be even greater, shouldn't it? Right? Because we're starting it with something that's already positively charged. I mean, it wants to hang on to those negative charges with like grim death, doesn't it? That means the second ionization energy, or when we remove a second electron in the gaseous phase, is going to cost even more energy. And then when we do it again to a doubly charged ion, to a 2 plus cation, it costs even more. And so the concept is this: as we rip electrons away from an element, it costs more and more and more and more energy. All right, as we start ripping them off. Now, here are the ionization energies for the first 20 elements. And what's cool about a table of ionization energies is that you can get some really good information from this table. Let me show you how you would do that. Let's go back to nitrogen. So, pretty fine print here, but nitrogen is shown right here. How many valence electrons does nitrogen have? Well, the electron configuration for nitrogen is helium, 2s2, 2p, 1, 2, 3. Okay, so that means that it has a total of 2 plus 3, or 5 valence electrons. The amount of energy required to remove valence electrons is always going to be less than the amount of energy required to remove core electrons. And so what you have to understand is that since nitrogen has 5 valence electrons, as we rip those electrons off, of course, the amount of ionization energy required to remove the first one is going to be less than the second and third, and so on and so forth. But watch what happens. Let's look. If we remove the first electron from nitrogen, it costs, 1,400 something kilojoules. Costs, double that to remove the second one. Then we remove the third one, which is around 4,600. Then we remove the next one. And you can see there's basically with these 4 values that I have underlined in red, even going to the 5th one, hopefully you notice that there's kind of a steady increase, right? It's kind of steadily increasing. But look what happens after the fifth or the last valence electron. We go to the sixth electron, and all of a sudden there's a huge jump, right, in ionization energies. Even if I didn't know that this was nitrogen, just by examining those numbers, when I see that there's a huge jump, I'm going to know, hey, it took, or the big jump occurred after after the fifth electron was removed. That means that this element has 5 valence electrons. Let me show you another example. Let's pick something even maybe a little bit simpler. Let's look at magnesium. Okay, if I look at magnesium, here's the first ionization energy. Here's the second one, it's about double. And then you see there's a big jump going from the second to the third. What does that tell you? That tells you that magnesium has 2 valence electrons. Let me prove it to you. If you look at the electron configuration for magnesium, it's neon 2s2. So it has 2 valence electrons. This is a graphical representation of what was on the previous table. Shows the variation of the first ionization energy with atomic number. So what's the trend for ionization energy as we go across a period? Well, if we look at, say, the second period, going from lithium to neon, you can see that generally speaking, it increases going across a period. Why would that be? The reason why ionization energy increases going across a period is because effective nuclear charge increases, which causes the atomic radius to decrease, and therefore the valence electrons are going to be held tighter, aren't they? Because they're closer to the nucleus. That's the whole answer right there. So as we go across the period, generally speaking, ionization energy increases. What if we were to go down a group, let's say? If we were to compare lithium to sodium to potassium to rubidium to cesium, well, the trend isn't as abundantly clear, but generally speaking, we see a decrease in ionization energy going down a group. Again, not as abundantly clear, but maybe it's a little bit more clear if you compare, here, 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 and here, like that, the halogens. The reason why ionization energies decrease going down a group is because atomic radius increases, doesn't it? And that's because principal quantum number increases. So as the electrons, or valence electrons rather, get further and further away from the nucleus, it gets easier and easier to remove them. So what do you notice about these alkali metals? Lithium, sodium, potassium, rubidium, and cesium. You notice that they have the lowest of the first ionization energies. That means they really are totally fine with losing an electron, aren't they? We know that because all the alkali metals like to form +1 cations. So what you're responsible for knowing is what's on this slide right here. The general trends for first ionization energies. Were there anomalies on the previous slide? Absolutely. The book goes into a little more detail about those, but you are not responsible for knowing every single anomaly, unless it's something that I go over with you in detail. So as we go across a period, ionization energy increases. And this is because effective nuclear charge increases, and electrons are held more tightly. The ionization energy decreases going down a group, or you could write it like this, that it increases going from the bottom to the top. The reason why is because the elements are getting smaller and smaller, and so the outermost or valence electrons are getting closer and closer to the nucleus. Nothing more than that. Well, with all that in mind, of course, we got to try a little problem here. This is example 8.4. We have some elements highlighted here for us on this periodic table, so they must be important. We have lithium and beryllium, and then oxygen and sulfur. First question asks us, which atom should have a smaller, lower first ionization energy, oxygen or sulfur? I'll throw that out there to my students. Can anybody tell me which one of these would have a lower or lesser, smaller ionization energy? Yeah, Trevor, you're 100% correct. It's sulfur, right? What's the rationale? It's sulfur because the 3p electrons, or the valence electrons, are further from the nucleus than the 2p, or the valence electrons, in oxygen. Let's write that down. Sulfur, this is what I put in my notes, because 3p electron, or electrons, are further, maybe I'll just write singular since we're just talking about the first ionization energy, because 3p electron is further from nucleus than the 2p electron, like that. Okay, next one says, which atom should have a higher second ionization energy, lithium or beryllium? Well, for this one, let's take a good gander at it. If we think about the electron configuration of lithium, lithium is helium, which is the core, and then 2s1. I'm going to rewrite that like this. I'm just going to write it out. 1s2, 2s1. Well, that means that when I start with my lithium, okay, if I remove an electron from that lithium in the gaseous phase, I get a lithium plus cation plus an electron. The configuration of the lithium plus cation is 1s2. If I take, and I keep forgetting the gaseous phase, if I take that lithium cation in the gaseous phase and I remove a second electron, now I'm going to have lithium 2 plus. But now what's my electron configuration? It's going to be 1s1 because I lost another electron. And so this electron right here, this was a core electron. All right. If I think about beryllium, kind of running out of space over here, but if I think about beryllium, maybe I'll write it like this, okay? Beryllium's first ionization energy, because beryllium is 1s2, 2s2. If I take beryllium and I make the beryllium cation, I remove an electron, its electron configuration is going to be 1s2, 2s1. That's the first ionization energy, isn't it? If I remove another electron from that beryllium cation, I get beryllium 2 plus an electron. Okay? What's the electron configuration of beryllium 2 plus? It's going to be 1s2. And so none of the electrons that were removed to form the doubly charged cation or beryllium 2 plus are core electrons. Whereas when I did this right here, I removed a core electron from lithium. And so lithium should have a higher second ionization energy than beryllium. And the reason why is just because core electrons are being removed in order to make that lithium 2 plus cation. Give me a thumbs up if you follow me on that idea. All right, thanks. Good. Great, as they say in Scottish. Well, let's look at, this is one of the last concepts I think that we're going to, one of the last major concepts in this chapter that we're going to look at, and that's electron affinity. What does affinity mean? You know, if you say, I have an affinity for donuts, what does that mean? It means you like donuts, right? If I have an affinity for, you know, a certain kind of music, it means that you like that kind of music. And so electron affinity is the desire or how much an element wants to gain an electron, right? It's basically the opposite of ionization energy, right? Because ionization energy, we were talking about removing electrons. Electron affinity is the negative of the energy change that occurs when an electron is accepted by an atom in the gaseous phase. All right. Well, it's the negative of that energy change. If we look at the energy change or the enthalpy of fluorine in the gaseous phase gaining an electron, you can see that it gives off a total of minus 328 kilojoules per mole. So we take the negative of that, and that's our electron affinity. So this is the measure of how much the fluorine wants that electron. If we look at oxygen, same thing applies. To make the O minus anion, we give off 141 kilojoules per mole, and so we would say its electron affinity is plus 141 kilojoules per mole. Well, the trends in electron affinity, I can tell you right now, they are not nearly as clear as the trends for ionization energy. And the reason why is because there's several factors that come into play when we look at the values for electron affinities. What I want you to know is that if we look at electron affinities that are in this table, and this is just showing representative elements in the noble gases, what's the first thing you notice is that the noble gases, they all have electron affinities of less than 0. That means they have basically no desire to take on an electron. Why would they? Because all of their valence shells are full, right? Whereas if we compare those to the halogens have some of the highest electron affinities on this table, if not the highest electron affinities. Why is that? Why would they have such high electron affinities? It's because all they have to do is gain one electron to become isoelectronic with the closest noble gas, right? They would all just have to gain that one electron. And so that's why the halogens have such high electron affinities. If you look at the electron affinities of, let's say, groups 1A and 2A, what are these? These are both metals, right? The alkali metals and the alkaline earths. You can see that they have really low electron affinities, don't they? Well, the main conclusion I would draw from that is that metals have lower electron affinities than non-metals, right? That seems to make sense to me because we've talked about how metals that are in group 1A like to form +1 cations. That would mean they has to lose an electron. We talked about how metals in group 2A like to form +2 cations. So why would they want to gain electrons? And again, you can see that in group 2A that the electron affinities are very low. Whereas the halogens, as we discussed, they all like to form -1 cations, don't they? And so they have higher electron affinities. Now, if you really get, and look at this table in detail and look at all these numbers and examine them very carefully, you'll see there's a lot of anomalies here. It's even more abundantly clear when you look at it in terms of a graphical representation. This graph covers elements number 1 through to barium, which is element number 56. Well, what do we see here? Generally speaking, as we go across a period, we see that electron affinity increases. It makes sense, right? And now you can obviously see there's a lot of anomalies here, but it does make sense, right? Effective nuclear charge is increasing. The elements want to become isoelectronic with noble gases. As you go across the period, well, they have to gain electrons in order to do that, whereas the metals have to lose electrons. And that's why non-metals, like the halogens, right, they have high electron affinities. So again, non-metals have high electron affinities, whereas metals like lithium, sodium, potassium, rubidium, and cesium, okay, those are metals, right? They're going to have low electron affinities. Okay, that's the general trend that you need to be aware of for our class. Let's take a look at question 8.5. Why are the electron affinities of the alkaline earth metals either negative or small positive values? Well, what do they have in common? They all have the same outer or valence electron configuration, don't they? They all are NS2. They all have a filled s orbital, don't they? Completely filled. Well, because they have that completely filled valence shell, NS2, they have little tendency to pick up an extra electron because it will have to go into a p orbital, which is shielded from nuclear attraction by the two ns electrons. Right? A p orbital is higher in energy, isn't it? It's bigger. And so once you have to start putting electrons into the p orbitals, right? This is the s block here, and this is the p block over here. Well, again, those electrons are going to be shielded from nuclear attractions by those s electrons, and so they're going to have very low electron affinities in group 2a. That's basically the answer. Now, it's more of a worded answer than a numerical answer or something that I could just circle. So if you need, I'm going to post a recording of this if you need to listen to what I said a couple of times. And the solution is also found in our textbook. Another interesting set of relationships in the periodic table that we won't go to in great detail, but what are called diagonal relationships on the periodic table. For example, if you compare lithium and magnesium, or beryllium and aluminum, or boron and silicon, these three diagonal, relationships here, you'll find that the elements actually have quite similar reactivities. The reason for this phenomenon is the closeness of their charge densities. So this is based off of charge, not change, charge densities of the cations that they form. So because of charge densities of their cations. Okay. Now you might be wondering, what the heck is a charge density, Mr. Dion? Well, charge density is the charge of an ion divided by its volume. So we could put that in here. Charge of ion divided by volume, like that. And cations that have similar charge densities tend to react similarly.